Okay, hello everyone. So let me just get this set up. This video is to review the challenge problems that were given on Wednesday night, so the 30th. So September 30th, the last SI session before your exam on Friday. These are the challenge problems from that evening. And because we don't have another session, this additional videos to go over them. Okay, now one thing to note, if you're kind of new to SI, if this is one of your first videos, I end every single session with probably between 5 to 8 challenge problems that I make. So these are problems that I think are exam difficulty or sometimes even more difficult than the exams to help prepare you. Um, so if you haven't done these, every challenge problem I've made up to this point covers chapters 1 through 3, which is covered on your exam on Friday. Now, do note that these are a mix of multiple choice and long answer. Just because something is long answer doesn't mean they can't make it into a multiple choice question, and vice versa. Also, just because I don't write a question on a particular topic doesn't mean that it won't show up on your exam. Everything I cover in SI and all the problems I've made up to this point tend to cover the topics that they cover most heavy on the exam. But again, they could ask things that I have not necessarily gone over or written questions about. And so here I just tried to make, I think it's 16 problems, kind of all the chapters, all the topics, and again, exam difficulty. How I'm going to kind of run tonight is I'll quickly show the problems. So it's about 2 at a time before looking at the answers. I'll just talk about what kind of topics the questions cover. And then I'll kind of say in 3 seconds, I'm going to go to the next slide, which has the solution. I'm just going to say that you have 3 seconds until I switch the slide in case you want to write down the question, get down more information, try it yourself. You can pause the video when I say that, so you have it as much time as you want. And then when you're ready to see the solution, you can hit play, and within a second or two, I'll show the answers. So here we have 2 classic chapter 1 problems that have to do with classification. And so number 1 is, what is the classification of magnesium sulfite? And number 2, it's kind of a word problem, but it talks about canker sore, and basically you're trying to wash your mouth out with salt water. You put too much salt in it, causing some of the salt to be undissolved, something called a supersaturated solution or a supersaturated state. And what is that classified as? Okay. So number 1 is a little bit more your traditional question where they tell you a compound, right? Magnesium sulfite, right? These are bound together through an ionic bond. And compounds, are pure substances that are, again, they have chemical bonds within them. So it's ionic or covalent bond. So in the case of magnesium sulfite, it's a ionic bond that links these 2 ions together. And it's multiple elements, right? It's not just one element making it a compound. Now, number 2 deals more with mixtures. So mixtures are substances that can be physically separated. Okay, and we have 2 types of mixtures. We have heterogeneous and homogeneous mixtures. Now, some people may have gotten thrown off and guessed homogeneous mixtures, right? The term solution is often hand in hand with a homogeneous mixture. But I want to show you why a supersaturated state is a heterogeneous mixture. So imagine trying to make a glass of salt water for your canker sore, right? And you dump too much salt in. I'm sure we've all done this at some point in our lives. And you can see salt granules at the bottom of the glass. That is what it means by supersaturated, okay? If it was not supersaturated, all the salt would be dissolved, okay? Now, if a solution is saturated or isn't saturated yet, it would be a homogeneous mixture. It's only because it is supersaturated that it's a heterogeneous mixture. So just to get into it, a homogeneous mixture is constant throughout, meaning every single point is going to be exactly the same. While a heterogeneous mixture, when you take one point to another, they're not necessarily identical. And so I kind of drew a cup with our solution. And again, those circles on the bottom are representing salt granules that didn't dissolve. And I kind of drew two squares showing two different points in this water that we made, the salt water, right? The top square, we can kind of see just a bunch of dots, right? That represents our ions, and they're pretty distributed equally. And then we look at a different square, right? A different point in this salt water where there are salt granules. And as you can see, they're not the same, right? Some have big chunks and others only contain ions. And because it's not the same from point to point, it is a heterogeneous mixture. Now, I purposefully made number 2 to try to throw some of you off, because again, the term solution typically means that it is a homogeneous mixture, but because it's supersaturated and there's remaining salt that didn't dissolve, that is why it's the heterogeneous mixture. So just watch out for little tricks like that. That really tests your true understanding of the difference between homogeneous and heterogeneous mixture. Okay. Number 3 deals with properties, so not just physical versus chemical properties, but intensive versus extensive. And then number 4 is a pretty classic long answer significant figure problem. One thing I would note about number 4, if you didn't see the SI session from Wednesday night, is that problem is much, much harder than they would give you on an exam. They would probably give you one of those fractions on the exam to solve out, not one fraction subtracted from another one. So if you can do number 4, you are probably more than prepared for a operations question like number 4. Okay, and so my answer to 3 as to what is the intensive physical property is C, that water is liquid at room temperature. Okay, when we look at option A, it says reactivity. Whenever you see the word reactivity, a little alarm should go off in your head telling you that that most likely indicates that it's talking about some chemical property, right? Reacting means that it's going to kind of change its identity to something new. And if you're kind of uncertain on what the difference between chemical and physical properties are, I did a complete run through tonight's session, Wednesday night session, of kind of all the topics between chapters 1 and 3. So I kind of give you buzzwords to help you realize what's the difference between a chemical and physical property. Now, options B, C, and D are all physical properties. They all have to do with the observable qualities of matter. But the thing that makes B and D incorrect is that they are not intensive properties, right? They talk about mass and volume, which are extensive, which means the mass and volume are dependent on the quantity there, right? If you take a if you take a solo cup and scoop up some random compound, let's just say water, the mass of that water will be different than if you pick up a gallon jug and scoop up water in that, right? Different amounts yield different masses. Same with volume, okay? But C is intensive. It's independent of mass, because whether you have an ocean, right, the Atlantic Ocean, or I'm currently holding a glass of water, right? My water is still a liquid water state, no matter whether I have the whole ocean or just my cup of water at room temperature. And so it's independent of mass, that state of matter, which is why it's an intensive physical property. Okay, so your answer number 4, as you can see, should have been 2 decimal points, and we'll kind of break it down. Just to talk about how I take an approach to these problems, I don't like to round my answers because it can affect, if you round too early, what your answer at the end is. And so I keep track of sig figs with by using arrows. Okay, and so that first 2 lines, those fractions, was just the original problem that I rewrote. Okay, and moving down to the next row, all I did was do any operation in the numerator or denominator that I had to. So when I hit the first fraction, I didn't have to do anything to the numerator. It's just 2.374. But I had to do some addition in the denominator. So I added those 2 numbers together and I got 12.649. But I have to be careful to make sure that I'm tracking my significant figures. So our rule for addition and subtraction for significant figures is we use the number of decimal places as the term with the least amount. So 0.639 has 3 decimal places, while 12.01 only has 2, which means our answer from that addition should really only have 2 decimal places, which is why I draw an arrow at the 4 to indicate that's where that number should end. But I personally keep the 9 there just so that when I do my division and later on math, my rounding doesn't affect my answer. Okay, so if I were to round that denominator number to the correct number of sig figs, it would be 12.65. But again, I draw the arrow and don't round to keep track of sig figs while getting the most correct answer possible. Now looking at the second fraction, the denominator is just going to stay the same, but we have subtraction in the numerator. So again, when we do subtraction, we take the number of decimal places as the term with the least amount. So 8.45 has 2 decimal places, while 8.0 only has 1, which means my answer in the numerator should be rounded to just 1 decimal point, which is why I put an arrow at the 4. But again, I keep the 5 after to prevent rounding errors. Okay, my next step is to go from fractions to just numbers, right? So I'm going to do the division that happens within these parentheses. So 2.374 divided by 12.649 comes out to 0.187683, right? I wrote it directly below. But I'm going to draw an arrow to indicate number of sig figs. So when we do multiplication or division, the rule is that our product or quotient should have the same number of sig figs as the term with the least amount. Okay, so now for multiplication and division, it matters about sig figs, not decimal points. So in the numerator, 2.374 is 4 significant figures. In the denominator, 12.64, right? I'm kind of stopping at the 4 because that's where my arrow is. It's telling me that that bottom number, although I have 5 non-zero integers, it should be 4 in terms of sig figs. And so I'm dividing 4 sig figs by 4 sig figs. And so I draw an arrow to that 6, telling me that the 0.187683 should really only be 4 significant figures. Okay. Going to the second fraction, we're dividing 0.45 by 7.72590. But see the arrow above that 0.45? That's indicating to me that that number should really only be 1 decimal point, which would round to 0.5, which is 1 significant figure. So although I'm going to plug 0.45 into my calculator, I have to keep track and note that the numerator is 1 sig fig, while the denominator is 5, which means my quotient from this division, 0.0582, if I were to round it to correct number of sig figs, would be 1 sig fig, and so it would round to 0.06. But again, I indicate this with an arrow rather than rounding. Now the last step here is to do the subtraction between 0.187 or so and 0.05 or so. And so I look at my arrows because again, we're doing subtraction, which means we want to round our answer to this subtraction to the same number of decimal places as the term with the least number. So looking at the arrows, my 0.1876 number should have 4 decimal places, while my 0.0582, the arrow indicates that that should only have been 2 decimal places if we were keeping track of sig figs the whole time, which means my answer from this subtraction can only really have 2 decimal places, which is how I eventually get to 0.13. Okay? And again, that one is a very challenging problem, probably much, much harder than you'd see on the exam. So if you struggle with it, that is okay. Okay, so number 5 is a accuracy versus precision question, along with a dimensional analysis and unit conversion question within the SI system, which is kind of like the metric system. So you're given information using a micropipette set to 125 microliters to add a compound to an empty vial to prepare for a reaction. The density of the compound is given. Based on the data, is it accurate, precise, both, or neither? Okay, so just about 3 seconds. I'll go to the answer slide. Okay, and the answer to this should have been B, that it's precise but not accurate. Okay, in that table, you're given mass of the vial, just an empty vial, and the mass of the vial along with the compound inside of it. So if you subtract the mass of the vial and the compound, or sorry, if you subtract the mass of the vial from the mass of the vial and the compound, right, you will get just the mass of the compound. And so I do that for each trial, and I get 0.133 grams for trial 1, 0.131 grams for trial 2, and 0.129 grams for trial 3. Now I could convert these masses to volume to compare it to the 125, which is really a comparison for accuracy, right? We want to compare it to the 125 for accuracy. But instead of doing 3 conversions, I'm going to change the 125 microliters to grams instead. So again, if you're using a micropipette, you should be dispensing 125 microliters each time if that's what it's set to. That would be your true or goal value, okay? But because we have it in grams, I'm going to convert so that we can actually compare them. So 125 microliters is kind of that U shape in an L, right? And 1,000 microliters are in 1 milliliter. And in case you saw the density, it was 1.4 grams per centimeter cubed. By definition, a centimeter cubed is equal to a milliliter. They're just the same thing. I wanted to throw that little thing in to see if you noticed and knew that. Okay, so centimeter cubed just means a milliliter. Okay, and 1 milliliter is 1.4 grams. What we find is 125 microliters of our compound should weigh 0.175 grams. And we can compare this true or expected value to the mass that we got from each of our trials. As you can see, the trials are very close to each other in weight, but they're not all that close to the true value that we want of 0.175. This to me is much too far off from the true value to be accurate, right? It's very close to our target value of 0.175, so it's not accurate. But because these 3 trials are so close together, you know, comparing them to one another, that means that they're precise. So that's how I knew the answer really should be B there. Okay. This one I'm actually just going to pretty much skip through its naming just because all the names are here and then my answers are after the arrows. Okay, so the first one, diboron disulfate. Sorry, that was supposed to say diboron sulfide. Okay, I wrote it wrong, but my answer's correct. So diboron disulfide, not sulfate. Would be, that's a classic covalently linked compound. And so you look at the prefix to know how many of each there are. So di is our prefix for 2. And so it's boron 2, sulfur 2. Again, diboron disulfide, which is what is in the question. I just rewrote it wrong. Okay, chromium 3 permanganate. So chromium has a 3 charge. Permanganate is MnO4. It's one of your polyatomics, and it has a charge of -1. And so the big key for an ionic compound like this is that our cation charge, the positive charge, and the anion charge, the negative charge, must cancel. So if chromium has a 3+ charge, we need 3 negative charges to cancel it out. And so that's how I know we need to have 3 permanganate anions. Okay. Hydroiodic acid. HI, I want to put a little asterisk next to this. I meant to write it. I do apologize for not. It should and really must say aqueous next to it. If it's HI gas, that is hydrogen iodide gas. HI aqueous is your hydroiodic acid. Remember, an acid always needs to be in the aqueous state. If it's not acid. Okay, at least in the terms of this class. Then magnesium dihydrogen phosphate. So remember, dihydrogen phosphate is one of your polyatomics. The dihydrogen part in front of it just means 2 hydrogens along with a phosphate, so it's H2PO4, and it has a charge of -1. So that needs to set or counterbalance the positive 2 charge from magnesium. So it's Mg H2PO4, and there's 2 of those dihydrogen phosphates. Okay, number 6 asked us to write the name of the compound given the formula. So the first one, again, is a covalent compound, so we're going to have to use our prefixes. So it'd be tetra nitrogen, because there's 4 nitrogens, and then hexoxide. Now you might see that I wrote it twice, one in parentheses, one in not. Honestly, I'm not quite sure if you have to drop the A of hexa, but I think if you included the A or did not, you would be marked correct. You know, it's the prefix hexa and then iodide, right? And so sometimes when the element starts with a vowel, you occasionally drop the vowel of the prefix. So an example of that would be monoxide and carbon monoxide. In this particular case, I'm not sure and couldn't really find it, but if you wrote either one on an exam, I believe they would get the point and would give you the points, okay? HCO3 minus, I wanted to try to trick you guys and see if you knew that that is not carbonic acid. Remember, all the acids in terms of, whenever we name an acid in this course, it will always have a neutral charge, okay? So the fact that HCO3 has a -1 charge indicates you do not name it as an acid. It is one of your polyatomics, and you can name it one of 2 ways. Bicarbonate, you'll see that a lot in bio, as it's a buffer for the blood, or hydrogen carbonate, okay? H3O-Br, that's hydronium, your H3O, it's a +1 charge. It should be one of your polyatomics. And bromide, it's just bromine, and you just add the normal suffix of "ide." MgCN2, that is magnesium cyanide. Again, you don't need to specify the charge of magnesium because it's an alkali earth metal, and we know that they have a charge of +2. Similar circumstances for calcium carbonate, CaCO3. So calcium has a +2 charge, carbonate a polyatomic, a -2 charge, and they balance. Okay. So number 8 is, again, kind of a multiple choice version of a naming question, because again, your exam on Friday will be multiple choice. And then number 9 is starting to get, well, naming's chapter 2, but getting into atomic symbols, so more of chapter 2. Okay. So number 8 is looking for very subtle differences, and do you know what it should be? Okay. And the answer to 8 should have been D. It was manganese 2 hypochlorite. Okay, you only ever use the prefix hydro, which I think options E and F did. You only use hydro when you have a binary acid. Okay, binary acids are made of 2 components. One is hydrogen, one is your other element. Okay, but this is not an acid. It's ClO minus is the anion portion, which is hypochlorite. Remember, ClO is hypo as the prefix and ite is the suffix. And so we just put it together, manganese 2 hypochlorite. Okay, that one was just trying to trick you because they're all so similar. And that's really it. Number 9, they asked you which of the following is true, and the answer should have been F, none of the above are true. So I believe option A was that there were 33 protons. When you look at a periodic table, Se, or selenium, has 34 protons. Okay, so 34 protons, so A is wrong. Based on the mass number, remember our mass number is the number of protons plus number of neutrons. Those should have added up to 81. Okay, and so if we know selenium is 34 protons, we could have found that we should have had 47 neutrons, which helped prove that B is false, because I believe B said that there were 48 neutrons. And then you were told that there's a charge of -1. So remember, charges are created by the gain or loss of electrons, okay? A charge never indicates a change in proton amount. It's always electron amount. So if you have a -1 charge, that means you have one more electron than proton, which means you would have had 35 electrons, making C false, okay? And because A, B, and C are false, D, all of the above would be wrong. And so, B, A, and B are wrong, along with E, all of the above are wrong. So yeah, it's F. Sorry if I kind of messed you up there. Okay. Number 10, again, is an atomic symbol question. It's just kind of a word problem, and it wants you to derive it itself. So they wouldn't be able to really ask this on a multiple choice, but they, in essence, could have options that this represents. And then number 11 is a periodic trend question. And so it's kind of asking what's chemically similar to arsenic and in the third period. And I will, about 3 seconds. Okay. So number 10, so I kind of write the listed information, and on the next slide, we'll go through 11. So we know it has a -3 charge and that there's 18 electrons. We also know that there's 20% more neutrons than protons. So if we know we have 18 electrons and have a -3 charge, remember charge is only created by the loss or gain of electrons, which means a -3 charge means we have 3 more electrons than protons, which tells us we have 15 protons. And so to find what element this is, we should look at the periodic table, look at the proton amounts, and 15 protons is always going to be phosphorus, okay? And so really, the last kind of portions we need to write the whole symbol is find our number of neutrons so that we can find our mass number. Okay, and so we're told the number of neutrons is 20% more than our number of protons. So if anything ever says 20% more, 30% more, you don't just put 0.2 or 0.3, you put 1.2, right? So a 20% increase is 1.2. Why? Because 1, if you just wrote 1.0, that means the same amount. And so 1.2 is a 20% increase. Do not just write 0.2, okay? And so a 20% increase on 15 protons would give us that we have 18 neutrons. So now that we know how many neutrons and protons we have, we can add them up to find our mass number. So 15 protons plus 18 electrons tells us our mass number should be 33. And all the way on the right, I have my full atomic symbol. So 33 as a mass number, 15 protons, P because it's phosphorus, and -3 because you need to include the charge. If you were to leave one element out of this, it would probably be your number of protons, right? That 15 you don't really need. It's slightly redundant because by writing P, which is for phosphorus, by definition, that means 15 electrons. So, 15 protons. And so I think it's better to write it, especially on an exam, but it's not necessary to have the 15 in there because by writing P, you're telling us it's 15. Okay, 11 was periodic trends. So arsenic, AS, it's in group 15. So this really testing, do you know what chemically similar means? And do you know the difference between groups and periods? So groups are columns on your periodic table, and groups contain elements that are chemically similar. Okay, so group 15 has nitrogen, and then below it has phosphorus, and then below that might be arsenic. Not really sure what's below that, but all of those in group 15 will be similar to each other chemically. Okay, so we know arsenic's in group 15, and it's also in period 4. Okay, but they said what is chemically similar to arsenic, which means it's in group 15, and in the third period. So all you have to do, period means row, you just look at the third period, and you'd find that the answer should have been B, phosphorus, which would have been on the table directly above arsenic. Okay, so this problem is a very, very, very classic combustion reaction. Okay, typically in this course, especially for problems like this, we see combustion reactions with an unknown molecule containing C, H, and O, It'll react with diatomic oxygen and will produce carbon dioxide and water. Okay, and they almost always give you grams of unknown compound that they ask you to solve for the equation for, right? So what's the empirical formula? They'll also give you grams of CO2 and grams of water typically. Okay, and in this case, they also tell you the molar mass of the compound, which plays into the very end. Okay, so this is all my work. I'm going to kind of walk you through it step by step. So at the top, I just wrote my equation and my given information, right? I write CXHYOZ because I don't really know the subscripts. Those are unknowns that we're solving for. Now, the key to this problem is we only see carbon in our unknown molecule in CO2, and we only see hydrogen in our unknown molecule in water. Now, due to conservation of mass, we need to have equal amounts of carbon and equal amounts of hydrogen on both sides, and that is the key to these problems. So we're going to start with 16.36 grams of CO2, and stoichiometrically find how many grams of just carbon we have, right? So it's 1 mole of CO2 is 44 grams or so. And in 1 mole of carbon dioxide, we have 1 mole of carbon. 1 mole of carbon is 12.01 grams. This tells us that on our product side and on our reactant side, we have to have 4.465 grams of carbon. And we do the same exact thing for hydrogen in water. Okay, so 6.700 grams of water, we convert to moles of water, then we convert from moles of water to moles of hydrogen, then from moles of hydrogen to grams of hydrogen, and we find that there is 0.7497 grams of hydrogen on the reactant and product side. Now, we know how much carbon, the 4.465 grams, is in our unknown compound. We know how much hydrogen is in that compound. So by knowing those, we can solve for how many grams of oxygen are in that compound. To do this, you take the total mass of the compound, which is the 8.190 grams, and we subtract out the mass of carbon plus the mass of hydrogen, right? And the remaining mass will be all oxygen. And so what we find is we have 2.975 grams of oxygen. Now, at this point, we have grams of carbon, hydrogen, and oxygen. And from here, we do a typical empirical formula question. Okay, so what we're gonna do is we're gonna write our amounts of each, so 4.465 grams of carbon, and I'm going to convert that to moles. So when I divide it by its molar mass, I have 0.3718 moles of carbon. I do the same for hydrogen using its molar mass and get that there's 0.7438 moles of hydrogen, and then I do the same for oxygen. 2.975 grams of oxygen is equivalent to 0.1859 moles of oxygen. The next step from here is to divide all of those moles by the least number of moles, right? So we have about 0.37 moles of carbon, 0.74 moles of hydrogen, and only about 0.18 moles of oxygen. So the moles of oxygen are the least number, and so we divide all of these numbers by 0.1859 to give us a small whole ratio number that is our empirical formula. Now, because none of these numbers are decimals, we don't have to multiply by anything. We just know our empirical formula is C2H4O. And if you calculate the molar mass of this, it is approximately 44 grams per mole. Now, we're given the molecular weight in the question. It said that our compound weighs 44 grams per mole, right? Second to last line, 44 grams per mole. Now you will take this number and divide it by the molar mass of your empirical formula, which in this case would be 44 divided by 44. The quotient of that, which in this case is 1, is what you multiply all your subscripts by in your empirical formula to get your molecular formula. So in this case, it's 1. So we multiply 2 carbons by 1, and in our molecular formula still has 2 carbons. Hydrogen still has 4, oxygen still has 1. Okay, whenever you do that division, if your quotient's ever 1, it means your empirical and molecular formula are actually the same. Okay. Number 13 is, this actually came from a student somewhat. Also, some students helped me make this by sending in problems during the session, so thank you. It at least gave me a basis to make some questions, but 13, a lot of it was obtained from a student, so thank you for sending that. It's basically a long dimensional analysis problem. Okay, and I'm going to kind of walk you through a strategy you can use in hard dimensional analysis problems if you get stuck. Okay, so you guys can kind of read that. And then number 14 is kind of a classic dimensional analysis problem using Avogadro's number. Okay, so I'm going to go to the next slide in 3 seconds. So again, if you need to pause it, feel free to do so now. I would definitely try number 13 on your own before looking at the answer. Okay, so to walk you through number 13, you might see I kind of have units at the top, and I'm gonna, if you ever have a problem and you have so many numbers you don't even know how to approach it really, sometimes I think units can be extremely helpful. Okay, so looking at the information, I'm eventually asked for how many dollars. Okay, so I know that at the end I need to get to money. Okay, and it says how much money does it take to extract 8 kilograms of titanium. That indicates to me that that's what I should start with in my conversions. And so below that, you'll notice I kind of filled in gaps. It's, okay, what can I do starting at kilograms of titanium that will help me get to money? Okay, and I kind of just write the general units. So from kilograms of titanium, I can pretty easily find just grams of titanium. And then perovskite or whatever is the titanium containing compound, right? It's CaTiO3, right? And I can convert from titanium to that molecule using moles, right? Whenever we convert from an element to a compound or between compounds, we can use our molar ratio to help us. And so by using moles, we can convert to grams of titanium to eventually grams of that perovskite compound, okay? Now, once we have grams of that compound, we can convert to grams of rock, right? Because it has a percent composition of the rock, and then we can go from grams of rock to money, okay? So let's look at these conversions. So we start with 8 kilograms of titanium. Now 1 kilogram is 1,000 grams, okay? And 1 mole of titanium is 47.87 grams. Okay, so up to that point, we have moles of titanium. But we don't care about titanium, we care about the solid, the perovskite thing. I don't know how to pronounce it at all. And so we look at that, and it takes 1 mole of titanium to make 1 mole of that compound. Okay, and if you add up to find the molar mass, 1 mole of that compound would be 135.95 grams. Okay, so this is how many, up to that point, if you were to cancel out all your units, that is grams of your perovskite, okay? And you're told in the problem that you extract this from rock, okay? And that it's 18.44% by mass, the rock that it's in, right? So it's 18% of the weight of that rock, which means if it's 18%, that means in 100 grams of rock, it is 18.44 grams of that perovskite compound, okay? So if we were to look at our units to there and cancel everything out and did all of our math, we would have at this point, the very end of that last dimensional analysis, just grams of pure rock. And then to get from grams of rock to money, it tells you that it takes $2.10 to drill 1 gram of rock. When you do that math and round to the next, the nearest whole dollar, comes out to $258,740. Okay. So again, sometimes if you're overwhelmed by the number of numbers, you kind of know what you should start with and end. Sometimes just look at your units. They can be helpful. That's not a strategy that works for everyone, but kind of practice it. See if that's something that can help you in a tricky problem. Okay, number 14, it's how many electrons are in 1.67 moles of fluorine, a fluorine ion or a fluoride ion. And so 1 mole is 6.022 times 10 to the 23rd atoms. Okay, whenever they ask you for how many atoms, how many protons, how many electrons, you're always going to have to convert from moles to atoms using Avogadro's number like I did there. Now, every single atom has 10 electrons. How do I know that? Fluorine, by definition, when we look at the periodic table, has 9 protons, and fluorine has a -1 charge here. It's an anion. Okay, the -1 charge means 1 more electron than proton. If fluorine always has 9 protons and has a -1 charge, it has to have 10 electrons per every single atom. You do that math, and it should come out to 1.01 times 10 to the 25th. Okay, here come our last 2 challenge problems for tonight. So number 15 will look kind of familiar to some of you. It's kind of solve for x. And then number 16 is a pretty straightforward limiting reactant problem. Okay. So just about 3 seconds, and I'm gonna go to my answer. So again, if you need to pause it, feel free to do so. And these answers are on 2 different slides. So we're told our percent composition of sulfur is 29%. And so I'm gonna plug this into our equation. So 29% sulfur is equal to our mass of sulfur over our total mass times 100, right? The 100 is just to convert it from a decimal to a percent. And this is just our percent composition or mass percent equation. Okay, and so on the next line, 0.29, right, I just divide both sides by 100, is equal to 2 times 32.06 over the total mass. Okay, now some of you might be confused, why is it 2 times 32? Well, 32.06 is our molar mass of sulfur, but the given compound, as you can see on the previous slide, has 2 sulfite ions, right? Hydrogen sulfite ions, HSO3. There's 2 of them to balance out the charge, which means there's a total of 2 sulfurs in this compound. And that's why it's 2 times 32.06. And again, the denominator's total mass. Through algebraic manipulation, we can solve and find that the total mass of this compound should be 221.1 grams per mole. But realize that this total mass still includes the mass of both bisulfite ions or hydrogen sulfite. They mean the same thing. Okay, so hydrogen sulfite or bisulfite, if you add it up, each one of those is equal to 81.07 grams per mole. And there's 2 of them, which is given in the formula, which means they contribute 162.14 grams per mole of this unknown compound. And so if we take the total mass, 221, and subtract out the sulfite mass, hydrogen sulfite mass is what I really should have written, was 162, we can find just the mass of X, which comes out to 58.96. Okay, so they ask you what's the identity, so you should be looking for something that's 58.9 to 59.0 grams per mole, and the best answer is cobalt. Yes, nickel is very close, but it's around 58.7. We're a little bit higher than that, and so the best answer for this was cobalt, and if you're rounding your answer to 3 sig figs, it should have been 59.0 grams per mole. Okay. Now this is the last one. Again, it's a limiting reactant problem. So I kind of just verbally in the problem described it. I actually didn't give you the formula. And a lot of people tonight during the session asked me how to balance an equation or how one starts that. And so it definitely depends on the equation to equation. And so one like this, my mindset is I looked at the most complicated compound in the equation, which for me, I kind of saw as iron chloride, right? 3 chlorines is kind of complicated. You know that you have to balance that. And so I kind of started with iron chloride. And what I said is, okay, if I have 3 chlorines on the product side, I need to have a 3 in front of my hydrochloric acid for my chlorines to balance. Okay, so that's how I get the second line. Now on the second line, I can see on the reactant side, because I now have 3 HCl's, I have 3 hydrogens on my reactant side. And if I looked at my product side, I have diatomic hydrogen. And so the only way to get 3 hydrogens on the product side is for my coefficient of hydrogen, or the diatomic hydrogen, to be 1.5. If you were on this second line to add up how many of each element there are on each side of the equation, it would be balanced, okay? There'd be 1 iron on both sides, there'd be 3 chlorines on both sides, and 3 hydrogens on both sides. The only reason you can't keep that second line as your balanced equation is you can't have decimals. okay, in a properly balanced equation. And so you're just going to multiply the whole equation by 2 to get your final balanced equation, which is why the coefficients are 2, 6, 2, 3, reading left to right respectively. Okay, now to get down to the actual problem. So we're trying to find what's the limiting reactant and how much hydrogen can we make. Okay, so if we have 45 grams of iron, we can convert that to moles of iron using its molar mass. And then from our balanced chemical equation, we know it takes 2 moles of iron, which is the coefficient in front of iron, to make 3 moles of hydrogen gas. The 3 moles coming from the coefficient of hydrogen gas in our balanced equation. Then 1 mole weighs a little bit over 2 grams. We can make 2.44 grams based on our iron. Now we do the same exact thing for 62 grams of HCl, right? We multiply it by 1 over its molar mass to find moles of HCl. It takes 6 moles of HCl to make 3 moles of hydrogen gas, and 1 mole weighs, again, a little bit over 2 grams. Now, based on our HCl, we can only make 1.71 grams of hydrogen gas. The HCl limits how much hydrogen gas we can make, which is how we know the HCl is limiting. And how much could we make? 1.71, right? You can't make any more than that because you run out of HCl. Okay, the last part said how much of each reactant do you have remaining? So whenever you're looking for excess reactant, I always start with the product we just solved for, right? We know that that we're going to produce 1.71 grams of hydrogen, okay? And that about 2 grams is 1 mole, and we're just going to work backwards. And 3 moles of hydrogen is 2 moles of iron. 1 mole of iron is 55.85 grams. Now, when you do this stoichiometry, this is going to solve for how much of your non-limiting reactant you used up. So this tells us how much of our iron we actually used, 31.6 grams. So to solve for excess, you take the starting amount of iron, which is 45 grams, you subtract the amount of grams you used, 31.6, and this gives you 12.4 grams of excess. Now to be proper, they asked for how much of both reactants, and so we'd have 12.4 grams of excess in terms of iron, and 0 grams excess in terms of our hydrochloric acid, because that is our limiting reactant, and your limiting reactant should always have 0 excess. Okay, so those are all the challenge problems. Again, all the ones I've given up to this point should be good. If you have any questions, concerns, comments, check out on the SI tab in the SI folder called SI information. There's a document with my contact information, also my office hours, which are the next 2 days. Feel free to email me questions. Just please don't try to overrun me with questions. I can only answer so many. And the ones that are really asking deep questions, really trying to understand it, I will try to do. So again, my office hours are by appointment if you have any questions. If there are any mistakes, please try to point them out so I can share them with everyone else. Because I do sometimes overlook things, so I apologize. And good luck studying.